Inorder Predecessor. Strange. Ah, so one of them is called the Inorder Predecessor, and one of them is called the Inorder Successor. Now, what does that horrible word mean? It's just, this is 20. If we look at the nodes in the tree, if we try to order them from smallest to largest, so the smallest is 4, and then 5, and then 7, and then 10, and then 15, and then 17, and then 18, 19, 20, 22, 25. If we try to order them from the smallest to the largest, this 19 is the element which is going to be before 20 immediately. And it's called Inorder Predecessor. So it's the element which comes immediately before this element if the keys are sorted from smallest to largest. The Inorder Successor is the element which is going to succeed this element immediately if the keys are sorted from smallest to largest. Okay, so if we order the keys from smallest to largest, then this is X, this is X, this is what is going on? This is X, this is the Inorder Predecessor of X, and this is the Inorder Successor of X. So the Inorder Predecessor is the node which comes before that immediately. I mean, okay, this might be confusing. It doesn't mean that it has to be, okay, imagine these nodes are 100, 150, 200, 170, 190, 180, 220, 250. Okay, so 190 is the element which comes before the element X immediately. Okay, in the ordering of the keys. Okay, not in the ordering of numbers. This is not 199. Okay, this is 190. It's called the Inorder Predecessor of this node here, and this one is the Inorder Successor, which is the element that comes immediately after this element. So these two nodes that you said we can use to replace this node when we delete it, they are called the Inorder Predecessor and the Inorder Successor. Okay, so let's not lose focus. We have seen lookup, we have seen insertion, and now we are looking at deletion of a dictionary implemented as a binary search tree. We have seen deletion of a node with 0 children, the deletion of a node with 1 child, and now we are looking at the deletion of a node with 2 children. And we are trying to of a node with 2 children. And we are trying to answer the question, which of the two, okay, which node are we going to use to replace Z? We cannot just remove Z because this will disconnect this part and this part. So we have to have a node here. So what is it? And you said that we can use either 19 or 20, and I said yes, these two nodes are special nodes. This is called the Inorder Predecessor, and this is called the Inorder Successor. So when we delete a node which has 2 children, we are going to replace it with the Inorder Predecessor or the Inorder Successor. This is dependent. I mean, it's up to you to do it. Okay. There is no one which is better than the other. When you program it, when you program deletion, it will be like delete. If node has no children, remove it. If node has 1 child, then replace it with this 1 child. If node has got 2 children, then find the Inorder Predecessor and replace it with it. Or find the Inorder Successor and replace it with it. Okay, there is no version better than the other. Okay, they are just the same. Now, we said, let's say we are going to replace with the Inorder Successor. So what happens? We put 22 here, right? And delete 22. Now, we are not we're not going just to delete 22 like this. This is also a delete operation. Now 22 has got how many children? 0 children, so we can just remove it, right? Now if we choose to replace Z with the Inorder predecessor, so we put 19 here, and then we delete 19. What kind of delete is this? Yeah, the node has one child. So how do we delete 19 in this case? We replace this with 18. Yeah, exactly. Now, so deleting a node with 2 children, we replace it with either Inorder successor or Inorder predecessor, and they are both the same. Replacing with Inorder predecessor means we have to delete the Inorder predecessor or delete the Inorder successor. We have seen the case where the Inorder successor has no, or one of them has no child, and the case when one of them has 2 children. Now, can the Inorder predecessor have 2 children? So, if this was 200, and that was 190, and that was 180. Okay, let's assume that. So what kind of child will the Inorder predecessor have? I mean, can you think of one? For example, give me a value. Can you think of one? For example, give me a value. 195. So you said the Inorder predecessor can have a child, and in this case is 195, right? Now, if this one has a child 195, what should be the Inorder predecessor of 20 or of 200? So what is the Inorder predecessor of 200? 195, right? So it's not 190. The Inorder predecessor cannot have a right child. The Inorder predecessor, by definition, cannot have a right child, because if it has a right child, it means this one should be the Inorder predecessor. Do you understand?
Yes.
Right? And the same for the Inorder successor. The Inorder successor cannot have a left child, because if it had a left child, this one is going to be the Inorder successor. That means the Inorder predecessor cannot have a right child, and the Inorder successor cannot have a left child. So the Inorder predecessor can only have one left child or 0 children. The Inorder successor can only have one right child or 0 children. In which case, deleting the Inorder predecessor or the Inorder successor is always going to be deleting a node with no children or a node with one child only. It can never be deleting a node with 2 children, simply because they cannot have 2 children at the same time. Is this clear? So this is for delete. We have seen the 3 cases. Now let's talk about complexity. What's the complexity of delete operation in this case? So the complexity of the first delete operation of the first kind. Okay, so we have first to go and find the node that we have to delete, and we know this costs big O of h. Now deleting the node is as simple as breaking the pointer, and this takes how much? Big O of 1, so it's big O of h in total for the first case. Now let's see the second case. Now the second case of delete, obviously we have to go and find the node itself. We do the lookup, it's big O of h, plus we said replacing the node with the child. And how long does it take to replace with the child? Big O of 1, because the child is just there. We just access the pointer and it's there. And then copy it over, which is big O of 1. It does not depend on the input, and so it's big O of h. So second case is big O of h. Now third case, we have to go and find the node, that's big O of h, and then we have to do what? We have to find the Inorder predecessor or Inorder successor, right? How long does it take to find any of them? Is it constant? No, because they can be something like that, right? This can be the one, right? No, this is the Inorder predecessor. It can be. It can be this, right? So we have to replace the node with that one. So again, in the worst case, we are going down H. So one big O of H for lookup, and big O of H for going down. Well, obviously, what you're thinking is, well, it's big O of H in total. It's not big O of H plus big O of H. It's like big O of H minus K plus big O of K or something. Maybe this is what you're thinking. It's not big O of H all the way plus big O of H all the way. It's not like that. But we are not going to think too much about it. We are just going to use the worst case. We are going to be pessimistic, okay? So we are going to say, look up, it's big O of H. It can go as long as the deepest node. And finding the predecessor or the successor is going to be big O of H as well. Now, once we find it, we are going to delete it. And deleting in this case is going to be category 1 or category 2. And we know both of them are big O of H. Okay, I see what you said, why you said big O of 1, because we have already found it. So there is no lookup involved, right? So because we have already searched for it, and we have found it in this big O of H, and now all we have to do is to delete the node. If it has 0 children, it's big O of 1. If it has 1 child, it's big O of 1. Yeah, so it should be big O of 1 here, because we have already, the big O of H is already included in this part. So in total, this is going to be big O of H again. Okay, so for deletion, what we have is 3 categories. Each one of them is big O of H. Now we have finished our deletion operation for all cases, and we have finished insertion, and we have finished lookup, and now we have our nice table again. So this is all blah blah blah, what I have said. And the code is going to look at the node. If it doesn't have any children, or if it has one left child, in which case, or one right child, or something like that, and finally when both of them are present, in which case we are going to find the Inorder predecessor. So in this code, I used find the Inorder predecessor instead of find the Inorder successor. I could have used the other one. Okay, we have not talked about how we find the Inorder predecessor. So we will go back to it in a moment. Oh well, it's now. Okay, before that, I just want to show the table. Yeah, so the table so far is this. Alright, so that's what we got. These are the dictionary operations, and for the binary search tree, what we did now is to have we got the complexity big O of H, and we know H is between log n and n. So now obviously the next thing we need to do is how do we force H to be log n, like we did, if you remember, in quicksort. We said the complexity, depending on the partitioning and depending on the choice of the pivot, it's either log n or n. And we said, so how are we going to? We need to force. We need to force the recursion tree to have depth log n. And this is why we came up with the idea of how about we use the median of medians, how about we use a random a choice, we choose the pivot randomly in order to give us this nice balanced recursion tree. So this is our next step of thinking. So the binary search tree is big O of h. It's still not what we want, because in the worst case it's big O of n everywhere. In the best case it's big O of log n everywhere. So the next thing is, how do we make sure that we are going to have big O of log n everywhere? So that's the next step. Now let's backtrack and see things about the Inorder predecessor and Inorder successor. So this is all blah 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 how you find them. In order to find the Inorder predecessor, all you have to do is to find the maximum of the tree. So what is this is a tree. What is the maximum value of the tree? Is the rightmost value. So the red tree, the maximum value is this, because it's the rightmost. We said this is a key, this is larger than it, larger, and this is the largest. So this is the maximum of the tree, and this is the minimum of the tree. So Inorder predecessor is the maximum of the right. The Inorder predecessor is the maximum of the right subtree. This is the left subtree. This is the left subtree. The Inorder predecessor is the maximum of. This is the left subtree. This is the left subtree. The Inorder predecessor is the maximum of this left subtree. The Inorder successor is the minimum of the right subtree. Okay, this could have been like that, blah. So finding the minimum of this subtree is going to be the Inorder predecessor, Inorder successor, and finding the maximum of this left subtree is going to be the Inorder predecessor. Okay, so in order to find the maximum of the tree, all we have to do is to jump. Always choose the right child until you find the maximum, and here always choose the left child until you find the minimum. Yes. Now here's another case for you to confuse you. So this is a nice case where the Inorder predecessor and the Inorder successor are obvious, and this is another case which might not be so obvious, right? This is starting to look like a snowman. Okay. So what I'm saying here is, this is node X, and this is the Inorder predecessor of node X. Is this right? Well, okay, it must be right because I've done it. Now, can you explain to me why it's right? Again, remember the definition of the Inorder predecessor. We said the Inorder predecessor, if we organize the tree, if we sort the keys of the elements in the tree from the smallest to the largest, the key of the Inorder predecessor is going to be the next smallest key. So the key of the Inorder predecessor is the one which is smaller than X and immediately before it. So there are two things. It must be smaller and it must be immediately before it. Now, is this smaller than this? It is smaller than this because this belongs to the right subtree of this node. And we know all nodes in the right subtree are larger than the node. Now, how do we show that it's the one which is immediately smaller? So we have shown it is smaller. Now, is it immediately smaller? To prove it's immediately smaller, one way is to show there is no other element between them. So, no other element is between them. So these elements cannot be between them. Why? They are larger than X, right? And X has nothing smaller than it. So this is the first smaller thing than X. So in this case, in order to find the in-order predecessor of a node X, what we do, if I go back here, what we said, we are going to go to the right subtree and always go right until we find it. In this case, in order to find the predecessor of X, there is no left subtree. There is no left subtree here, so we cannot apply the previous rule. So what we do, in this case, the in-order predecessor must be up. So we go up, and the in-order predecessor is the first element to the left. So we keep going until we find the first element to the left, and that will be the in-order predecessor. And a similar story for the in-order successor. Here we said, to find it, we are going to go to the right subtree and go left to find the minimum. Here, there is no right subtree. So what we are going to do, we are going to go up, and then take the first right, and that will be our element. Obviously here you need extra pointer to the parent. Okay, in the when we explained the different operations, insert, lookup, and delete, we did not have a pointer for a parent. So here you need a pointer to go up the tree. So this is how we find the in-order predecessor and the in-order successor. And there is one last thing to do with the binary search trees, which is Inorder Traversal. So Inorder Traversal, So Inorder Traversal, what it says, basically we have a tree of elements, and the Inorder Traversal is going to visit the elements in the order of their keys, from smallest to largest. So an Inorder Traversal of this tree is going to visit node 4, and then 5, and then 7, and then 10, and then 15, 17, 18, 19, 10, 11. This is the in-order traversal of this tree, from the smallest key to the largest key. That's supposed to be an 8. Yeah. And the code to do that is, I can't be bothered. Basically, it's a recursive call. Oh, I have to show it. So that's the one. This is called the in-order traversal. I call the function print in order. So that's the function that we want. So what it does, it's print in order is going to start from the root. So this function is going to print the keys from the smallest to the largest. You don't have to print them. I mean, you can access them, process them, get the data out of them, etc. Here we are just printing them to show how the procedure works, but you don't have to print the nodes. You can do anything. So the procedure calls itself over the left subtree, and then prints the current key, and then calls itself over the right subtree. Okay. So yes. So we start with print in order right here, and we said it calls itself over the left subtree, and then calls itself here, and then calls itself over the right subtree. So 1, 2, 3. So what it means to call itself on the left subtree, it calls itself over this node. And again, it applies the same trick. It calls the left subtree, and then itself, and then the right subtree. 11, 12, 13. So what does it mean to call itself over here? It is going to call itself over the left subtree, which is empty, over itself, and then the right subtree, which is empty. The procedure stops calling itself when it reaches the null pointer. So here it's going to reach the null pointer, so it does nothing. And then it prints itself, so it prints 4. And then calls itself over this null pointer, and it does nothing. Okay? And then what it does, after we have finished this recursive call, 11, we are going to do that, so it prints 5. And then we said it calls itself over 7, which means it calls itself over the null pointer and does nothing, prints 7, and then calls itself over here and does nothing. And then goes back to 10 and prints 10. And then goes now to this right subtree. Calls itself over here. What does it mean? It calls itself over the left subtree. It's null, so it does nothing. And then it prints 15. And then it calls itself over this, which means it has to visit this tree. The left-hand side here is empty, so it does nothing. And then prints 17. And then it calls itself over this, which means it calls itself over that, which means it calls itself over the empty, which does nothing, and then prints 18, and then prints nothing, and then prints 19. And then we have finished with that, we print 20. And then we call ourselves recursively here, which means we go there, which means we go to the empty and does nothing, and do nothing, and then we print 22. And then back to here, print 25. And then go back down here, it's an empty pointer, so it prints nothing. So at the end we have printed the keys 4, 5, 7, 10, 15, 17, etc. And that's how Inorder Traversal works. You can look at it in your own time, hopefully with the help of this video. Try to trace it by hand. Try to trace by hand how this code actually works in reality. The complexity of this operation is big of n because we are visiting n nodes in the tree. There is a little bit of log n, which is like we said, the log n associated with the recursion, etc., but it's absorbed inside the big of n. Okay, so what we have seen so far, we have seen a dictionary, and we have seen that these operations kind of are not appropriate for the dictionary, and then we started looking at trees. We discussed trees and different operations, and these different operations are going to be executed executed in big of h, where h is between log n and n. We have seen different operations that come in handy in doing deletion, such as finding Inorder Predecessor, finding Inorder Successor, finding the maximum, finding the minimum. The Inorder Traversal is something that we are going to see at the end of the lecture, not now. So far, binary search tree holds the most promise if we manage to make the depth of the tree log n instead of n, because right now it still has worst case complexity of big of n. So if we manage to make the depth of the tree log n, then we have managed to implement the dictionary quite efficiently. We're going to stop here. Next time we're going to finish the last part on AVR trees and start hash tables. Do you have any questions?